Hello dear student, today I am going to discuss about colligative property. I am Vikash Kumar, chemistry teacher. What is colligative properties? Those properties of solution which is dependent on total number of particles of solute. Total number of solute particles. I will discuss about definition of colligative properties. Colligative properties, those properties of solutions which is depended on total number of solute particles, but it is not dependent on density of particles. Now, particles may be atoms, may be molecules, or may be ions. You can take a screenshot. Now we will discuss about four type of colligative properties. First, lowering of vapor pressure. Second, elevation of boiling point. Third, depression of freezing point. And fourth is osmotic pressure and osmosis. One by one we can write the four colligative properties. First is lowering of vapor pressure. Second is elevation of boiling point. Third is depression of freezing point. And fourth point is osmotic pressure and osmosis. So you can take a screenshot. These are the four colligative properties. Now I am going to discuss about Raoults law of lowering of vapor pressure. According to Raoults law of lowering of vapor pressure, relative lowering of vapor pressure of solution. Now from Raoults law of relative lowering of vapor pressure is equal to mole fraction of solute. So with the experiment we can easily understand what is lowering of vapor pressure, what is relative lowering of vapor pressure. So with the help of these experiment, like this Raoults law is applicable for those solution which is composed by mixing of solute. It means non-volatile solute mixed with volatile solvent. Now with example we can understand solute may be NaCl and solvent may be water. Water is completely volatile because after heating water transforms into gas, vapor, but NaCl after heating cannot transform into gas. So these two examples are very good example of non-volatile and volatile component respectively. Now with the experiment we can observe Bell jar experiment, we can understand. Whenever a container is filled by water, okay, and This is bell jar, figure A, and another figure we can draw, and another figure we can draw again bell jar. This container is again filled by mixture of volatile and non-volatile components. So NaCl plus water. Okay. Then here pure water. Pure water is present at same temperature. This figure is figure B. So at same temperature, whenever A component and B component heated at same time, then we can observe large number of molecules vaporize from outer surface of water in figure E, in figure A, and in figure B at same temperature relatively less number of vapor molecules strike at top wall of bell jar. Okay, so this is called bell jar. This is formed by glass. This is also formed by glass. Now we can easily observe vapor pressure of A is greater than vapor pressure of pure component. So we can write here vapor pressure of A is more greater than vapor pressure of B. Okay. So this phenomenon is called lowering of vapor pressure because maximum vapor molecules is here. So vapor exerted by molecules maximum in A but relatively minimum in B. So due to relatively less vapor molecules or less vapor pressure, this process is called lowering of vapor pressure. Or now mathematically we can understand what difference between lowering of vapor pressure and relative lowering of vapor pressure. So you can take a screenshot. Now we can write here, let vapor pressure of pure component is P naught, vapor pressure of solution is P. So lowering of vapor pressure is P naught minus P. Okay, because P naught is more greater than P. Okay, now relative lowering of vapor pressure is pressure is P naught minus P divided by P naught. Now for the mole fraction of solute, let a small n number of moles of solute, capital N number of moles of solvent. Now we can write here mole fraction of solute. It means x of a small n is equal to a small n by a small n plus capital N. Now you can take a screenshot from Raoults law. Now from Raoults law. Now from Raoults law, lowering of vapor pressure is P naught minus P by P naught is equal to x of a small n. So in place of mole fraction of solute, we can write P naught minus P by P naught is equal to a small n by a small n plus capital N. Now you can take a screenshot. Now I can remove these contents and now with the help of these formulas we can write P naught minus P by P naught is equal to a small n by a small n plus capital N. This part mole fraction of solute. This part relative loading of vapor pressure. So this is Raoults law equation. Now let for very dilute solution n is 0, then we can write P naught minus P by P naught is equal to n by capital N. So this is formula of Raoults law. Now n is equal to number of moles of solute. So number of moles of solute is equal to W1 of solute by molar mass of solute. Okay, given mass by molar mass. Okay. Now capital N is number of moles of solvents. W2 by M2. Here W2 given mass of solvent and M2 molar mass of solvent. Now after putting these parts, we can observe formula become change. P naught minus P by P naught is equal to W1 by M1 into W2 by M2. Okay. Now you can take a screenshot